Here we have buffer and here we have no buffer. If we add acid, then these will pick up the protons. But here, 4 free protons are added. If base is added, very similar situation. 4 proton, they will be picked up 0, 0 in both cases. But here someone will donate the proton. But here, there is no one to donate the proton. No one to sacrifice their own proton. Hello, I am Dr. Azaz from MedicoVisual.com, and in today's visual lecture, we will discuss the concept of pH buffers. And this is the most important lecture of this lecture series on pH and acid-base balance. The concept of pH buffers that we will learn today will set up a basis to understand the clinical and other topics that will come up in the later lectures. So please watch this lecture very carefully, otherwise you will not understand the other upcoming lectures. So before discussing the pH buffers, let me tell you a story that there was a scientist named Robert F. Pitts, and he did something very horrible with a dog. That he took a dog, he removed the kidneys of the dog, and then he measured the pH of the dog. Let me pause this video. This is AI generated video that I created for this lecture. So before doing anything, he measured the pH of the dog, and of course the pH of the dog, this normal healthy dog, was found to be about 7.44. Then what he did is that he did something, as I told you, horrible, that he injected about 150 milli equivalent of strong acid HCl into the body of this dog whose kidneys are already removed. So he injected acid into the body of this dog. Such a horrible thing to do. But what he noticed is that after injecting this HCl into the body of dog, the pH of the dog dropped only to about 7.14. So there is about 0.3. So there is about 0.3 units drop in pH. So this is not much dramatic, to be honest. There is the drop in pH, but it is not that much. Let me tell you why. Okay, so let's understand this concept. Here, you know, the body water, the total body water of dog is about 11.4 liter, right, of an average dog. So its pH is 7.44. But if we take the distilled water, the pure distilled water, and 11 liter of this distilled water, the same amount of 11.4 liter, the same amount of distilled water, if we take it, and initially we are measuring the pH of both of these. So here we have pH 7.44. For the distilled water, it is pH is 7. But what we do is that we add 150 milli equivalent of HCl in both of these solutions, in the blood of the dog as well as in the distilled water. What will happen? So you see what happened here. From 7.44 to 7.14, only 0.30 units drop in pH. But here you see what happened here. Initially, if we talk about the pure distilled water, the pH was 7. It dropped to what? 1.84. Such a huge drop in pH. How many units? I am not gonna count, but it is about approximately 5 units. So 5 units drop in pH versus 0.30 unit drop in pH in case of dog. And this is not just the case with dog. It is true for humans as well. This initial experiment, fortunately, it was not performed on humans, but the situation is same in humans as well. There is very little drop in pH when a strong acid is added to our blood, or even a strong base is added. There is very little drop or raise in pH. The reason being that there is something in dog as well as in human, something in the blood of the dog as well as in human, which resists the change in pH when a strong acid is added as well as when a strong base is added. So what is that something that resists the change in pH when a strong acid as well as when a strong base is added? That something is pH buffer. So what is pH buffer? pH buffer is a solution that resists a drastic change in pH. So this is first part of definition. pH buffer is a solution which resists a drastic change in pH when a strong acid is added as well as when a strong base is added. So both of the things are involved here. It resists a change in pH against acid as well as against the base until it is used up. This is important. So you compare it with enzyme. Enzyme, they speed up the reaction without being used up themselves. But buffers are different. They themselves get used up. They are selfless. They prevent drastic changes in pH, like you know like the suspension of your car. So I hope you got the concept, but they do get used up themselves. This is important. They do get used up themselves. So it means that we need to reclaim the components of buffer that we will discuss in the upcoming lectures. That how do we reclaim or how do we heal the buffer, as I say it like this. This is not an official jargon or official word, but it helps you understand. But anyhow, this is the complete definition of pH buffer. It resists drastic change in pH when a strong acid is added as well as when a strong base is added until it is used up completely. So this is pH buffer. Now to understand the pH buffer, let's go back to our concept of acids and bases. So in our lecture on the basic concepts of acid and base, I told you that let's assume we have a chair, a nice cute chair, and on this chair Mr. H is sitting. Now if we throw this chair in water, something strange happens, that spikes arise from this chair. So naturally Mr. H will jump out of the chair. So what is this chair Mr. H complex? So this chair Mr. H complex is acid. We write it like this. This is the general formula, HA. Now H is the common component, Mr. H, which is a proton, H positive, and A is the chair. It could be anything. For example, in case of H, if we have HCO3, then what we call is H2CO3, carbonic acid. So this is an acid. For example, if HCl, then the Cl part is the chair and H part is of course H. It is consistent across the acid. All acid must have at least one H. They may have more than one H and they are called polyprotic acid. We will not go into that. That is pure chemistry. But anyhow, at least one H must be present, that it must be able to donate, right? So in simple terms, in aqueous environment, what is the definition of acid? In aqueous environment, a substance, a chemical which donates its proton in the aqueous environment, that chemical, that substance is called acid. So acid, when it is thrown in water, it releases this H positive. This is the simplest and easiest definition of acid. And what is the base? Base is like this fancy comfortable chair. Here we are also having this chair. Here we also have this chair, but this chair is much more comfortable. So when this chair is thrown in water, very few spikes arise, right? So this chair picks up the proton that are inherently present in water as well. So two things might happen. You know, water is partially ionized, so some protons are already present in water. But it is not just that. This chair can actually ionize water and steal the protons of water's own proton as well. Again, I will not go into that much chemistry, there is too much to it, but I hope you got the basic concept. What is an acid? Acid is substance which gives proton or donates proton in aqueous environment. What is a base? Base is a substance which accepts proton in aqueous environment. Simple as that. Now, we need to understand the concept of strong and weak acid. So simply put, we have these two chairs. So this metallic chair, which is already hard, strong, rigid, very little space to sit, already very uncomfortable, let's call it chair A. And this chair is chair B. So this chair is chair B. It is already very comfortable, easy to sit, already a good area to sit here. Along with that, only small spikes arise from it when it is placed in water, when it is thrown in water. Here, very huge, big spikes arise when it is thrown in water. So my question is that if Mr. H has to sit on one of these chairs, it has to choose the chair. Which chair it will choose? Chair A or chair B? I hope your answer would be chair B because it is comfortable chair. So it means that this is a strong base. A strong base is one which can easily pick more proton, and the chair is not chair actually. Strong base is a chemical or substance which can accept more protons, simply put, compared to a weak base. This is very weak base. It is so weak that it is not even a base. Why I'm telling you suddenly about the base? Well, there is a reason for it. If we go back to this acid part, so now observe this something unique here. So here you see we have this chair. It is still having some spikes. It is not very comfortable. But what actually happens that if lots of Mr. H are sitting here in water, if there are lots of Mr. H, then what will happen that too many Mr. H, they do not like to roam free here. So some of Mr. H, even when they do not like to sit on this spiky chair, they will still sit on this spiky chair, and they will become again acid, right? So basically this chair is, if you look carefully, this chair itself is acting as a base because it is accepting a proton. So what is the definition of base? Base is something which can accept a proton. So this chair is actually acting as a proton because it is accepting. No, it is not acting as a proton. I mean, this chair is acting as a base because it is accepting a proton. So what is happening here? So let's suppose this is HA, this is acid. If it dissociates into H positive and A negative, this A negative can accept proton and can go back into HA. It can again form acid. But this does not happen usually when it is balanced. Actually, it does happen, but the net result is same. We will not go into that. For practical purposes, it mainly happens as a net result. It mainly happens only when too much of these substances are present. It means the equilibrium is disturbed, if you know a little bit of chemistry. So let me give you an example. For example, the acid is H2CO3. So it will dissociate into H positive plus A negative, not A negative. Here the A negative is actually HCO3 negative. Now if there is too much acid, too much proton, I mean, if there is too much proton, this chair HCO3 is like a chair. This chair can take up this proton, and it can go back into H2CO3. What I mean by this is that H positive plus HCO3 negative can combine back to form H2CO3. But what if this chair has lots of spikes? It's a big, big, rigid chair, uncomfortable chair, metallic chair. Okay, let's go to that diagram so it's easier for you to understand. Let's suppose that here is we have this chair A, this big spiky chair. This chair is like Cl negative. So it is big spiky chair. Can it accept a proton any significantly in any significant amount? The answer is no. So that is why when we write HCl, dissociation of HCl, a strong acid, we write it like this. We do not write it like this. We do not write it like this. We write it like this. This is irreversible. So HCl will only go in this direction. So even when there is lots of H positive, it will always, it cannot go back in the reversible direction in a significant amount, right? So out of billions or trillions of molecule, if one of the molecule, one of the H positive is daring enough to sit on that chloride, we will just ignore it. But it does not happen significantly, right? So HCl, it releases H positive, and then the Cl is like this spiky chair. It does not act as a base. So what's the point here? The point is that if I go here, so here the H2CO3, when it dissociates, let's write it again because it is, the diagram is being congested already. So let's write it here that H2CO3, when it dissociates into H positive plus HCO3 negative, this HCO3 negative can act as a base to form this acid. So basically an acid dissociates into a base, and this base is called conjugate base of this acid. So this is conjugate base of this acid. So HCO3 negative, the bicarbonate ion, is the conjugate base of the carbonic acid. If it was HCl and it formed H positive plus Cl negative, can we call this Cl negative conjugate base? The answer is no, because for all practical purposes it cannot go back any significantly. I hope you got my point. So why I am teaching you all this thing in the lecture of buffers? Because it is very important to understand the pH buffers. Let me show you. So here we are doing something very interesting. So here we have lined up some empty chairs, and we have lined up some chairs that are filled with the Mr. H. So what is this situation here? Actually, this empty chair is like A negative, or for the sake of example, we can say HCO3 negative. Of course, it can be any base, any conjugate base. And this is a weak acid, for example, HA. Or HA is of course not the actual acid. HA is just a placeholder. The actual could be H2CO3, right? So we have some almost equal amount of, let's say, the acid and almost equal amount of its conjugate base. So acid, as you know, a weak acid, it dissociates into its conjugate base. So if we have equal amount of weak acid and its conjugate base, and of course here we have inherent protons of water. Water of course releases its own proton. That is why water has its own pH, which is considered neutral pH, that is 7. So what happens? Let's suppose we add a strong acid here. So let's suppose we add HCl. Now HCl will immediately release the proton, and these protons cannot significantly dare to sit back on these chloride ions. So these chloride ions, they are not doing anything, they are just lying there as a bystander looking at the situation, that what is going on there. So they are not doing anything in terms of pH. So these chloride ions, they do not increase the pH or they do not decrease the pH. They do not have any effect on the pH. So what thing affects the pH? That is these protons. So as soon as these protons, they jump into this solution, they will, they might actually immediately decrease the pH. As you know, pH is the negative log of hydrogen ion concentration. So these protons, freely lying proton, this free proton in water, they will immediately decrease the pH of the solution. So that is a problem. But we have these things, these empty chairs. So these protons can sit on these empty chairs, and now, because they are no more free in this solution, they are not freely lying in this solution, the pH will remain unchanged. But Dr. Azaz, in our original example, we had seen that the pH actually changed from 7.44 to 7.14. There is decrease in pH of 0.30 units. Although this change is small, but still there is change in pH. But here you are saying that these chairs, they pick up all these acids, so there should not be any change in pH, right? But still there is change in pH. So what is going on here? I know you might be confused, but let me tell you what is happening. So the situation here is that the protons, the HCl was added here. The HCl uh, initially tried to decrease the pH drastically because it released free proton in water. But these empty chairs, which are basically HCO3 negative, so HCO3 negative picked up H positive. This is the reaction going on, and it formed H2CO3. Now the thing is that this H2CO3 is, what is this? It is not a neutral substance. It is an acid after all. Although it is a weak acid, but it is still an acid. It is not a neutral substance. It is still an acid. So what actually happens, that the amount of H2CO3 raised. So because H2CO3 is a weak acid, what is the definition of a weak acid? A weak acid is an acid which does not completely dissociate in water. Okay, let me clarify it a bit more to you, because I know some of you might be confused here. So here is a strong acid, let's say HCl. Okay, let me make some chairs of HCl, some simple chairs like this. Lots of chairs. Right? So on these chairs, of course, Mr. H is sitting like this. This is HCl. Now on another side, we have H2CO3. And these chairs are somewhat comfortable chairs. Let me draw it with this color. How should I draw these chairs? Okay, I am gonna do something differently, that I am gonna copy this to save your time. So we have these lots of chairs, and this is, let's say, H2CO3. I think it's enough. Or should I draw more? Okay, let's draw a little bit more. We can copy all these together. Where did it come from? So anyhow, so now initially we have Cl sitting on all these chairs, and then we have also protons sitting on all these chairs. When they are thrown in water, when these acids are thrown in water, because it's a H2CO3, okay, let me write it. This is H2CO3. Because this is H2CO3, it is comfortable chair. Most of these protons here, they will keep on sitting on these chairs. Only some will be released in water. So let's say two protons will be released in water out of all these, for just for the sake of example, right? So others will, even in water, even if some small spike arise from these chairs, they are unbothered, because these chairs are still comfortable. They do not want to float in water. They do not want to jump in water. They keep on sitting on these chairs. But here we have these big spiky chairs. So almost all the H positive that will jump from these chairs, from HCl, all these will jump from this chair. So what will happen that there will be lots of free H positive. Almost all of the H positive will be free inside water, almost all of it. Okay, maybe one of them might be keep on sitting on this chair, that might be daring enough to continue sitting on this chair, but all of them, they jumped out into the water. But compare this, they are still there. So it means that H2CO3, it is not all of them, not all of the H2CO3 molecules are converted into H positive plus HCO3 negative. Many of them, they are still undissociated in this form. This is undissociated form. This is dissociated form. Many of them, they are still undissociated. So weak acid dissociates incompletely, but compare this with a strong acid which dissociates almost completely. The strength of acid depends upon how strongly it dissociates in water. The more it dissociates, it means the more proton it donates. So we can say it like that: the strong acid donates more proton in water as compared to the weak acid. Now again, why I am teaching you this thing? The thing is that this diagram is okay, let me show you where it is. Yeah, so this diagram is much more simplified. We are only showing these four acids here. Actually there are billions and trillions of molecules. Maybe I have never counted them how many they are, but they are many, to be honest. So here we have these just four sitting here. But when there are millions and billions sitting on this chair, of course, some of them might jump back into water, right? So it means that when they will jump back into water, the pH will decrease. But because it's a weak acid, not all of them will jump. Many of them will keep on sitting on these chairs. So what actually happened here? this is basically the buffer. This situation is this, these two components are the components of buffer that I will review at the end as well. So basically what buffer actually did, buffer took the strong acid and converted into weak acid, converted into very weak acid. So because of conversion of weak acid, the pH change is very nominal. It is not drastic. There is change in pH. It resists the change in pH, right? It resisted the change in pH. It is not like that it will completely prevent the change in pH. No, 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 not like that. There is change in pH, but there is minimal change in pH because the strong acid, all these free protons which would have drastically risen the pH, not risen, which would have drastically decreased the pH, this is mitigated because they are converted into weak acid. So some of out of these millions of weak acids, some of the protons will still remain in water, some of them will jump in water, some of them will dissociate, but the pH change will not be very drastic. So now these are more acid is formed, right? So again, if this situation continue, more acid will come. Ultimately, a time will come that we will only have these chairs, and then we will only have this acids. Then if more acid come, then there will be nothing to resist the change in pH. So the buffer would have been broken. So that is why I said that buffer do get used up themselves. So buffer needs to be healed. So if we compare that, if a strong base is added, let's suppose NaOH. So out of, let's suppose initially we have Na here, but sodium will jump in water and sodium won't do much here. It's a normal component of our blood. Again, it will be sitting here. Mainly this is OH negative, let's suppose, which is causing problems. So OH negative is like a very comfortable chair. It is so comfortable that it will steal the protons of even water as well. So if the water's proton are stolen or solution's proton are stolen, what will happen? The pH will increase. So then here our beautiful HA or H2CO3 or whatever the buffer is, they will donate, they will sacrifice their own proton, they will donate their own proton. So these OH negative, they had stolen 4 protons, so 4 protons will be donated by this, right? But the problem again is that they are converted into this form, the conjugate base form. The acid is converted into conjugate base form after fighting with these bases, right? So this is the problem. Again, it needs some healing. So if you compare this situation, that here we have buffer, here we have buffer, and here we have no buffer. What will happen if we have buffer? So if we have buffer and we add acid, then these will pick up the protons. The conjugate base will pick up the proton. So ultimately the free protons are still 4. There is no change. But here 4 free protons are added. It means that there will be drastic change in pH. Let's see it again. So initially 4 protons here, 4 protons here. Let's remove this. So initially we have 4 protons here, 1, 2, 3, 4, 1, 2, 3, 4, right? So here there was no buffer, here there was buffer. So HCl added, again 8 protons, 8 protons. But here this picked up the protons, conjugate base picked up the protons. So number of proton went back from 8 to 4. So it started from 4, then raised to 8, and then again to 4. Actually this happens in fractions of second, not even seconds, maybe nanoseconds. It happens very quickly. So you don't notice a drastic change in pH when the buffer is present. So this is the comparison of buffer with non-buffer. If base is added, very similar situation. 4 proton, they will be picked up 0, 0 in both cases. But here someone will donate the proton, but here there is no one to donate the proton, no one to sacrifice their own proton, right? So here there will be again 0 proton, but here the situation is just like that, just like the original. Let's watch it again. So it's very easy to understand, isn't it? Now, if you look carefully, we have these two components of the buffers. We have this conjugate base, and conjugate base is actually fighting with the strong acid. And here we have acid, weak acid, which is fighting with base, a strong base. So basically we have these acid fighting soldiers and we have base fighting soldiers. The acid fighting soldiers will give the chair to extra protons that come here, so there won't be drastic change in pH. And we have these base fighting soldiers which donate the proton when base is going to steal the protons of this solution, the inherent protons of this solution. So we have these two soldiers, and situation is very interesting here. Here, while fighting, unlike the traditional soldiers which unfortunately die while fighting, these soldiers, they do not die, they convert from one form to another, right? So when acid come, acid sit on these chairs and they are converted back into this form. And if base come, these protons are donated, they convert back into this form. So basically their balance is disturbed, and this balance must be fixed by some mechanism. As it turns out, in our body, the most important buffer is H2CO3, HCO3 negative buffer. And here we have the H2CO3 is coordinated with the carbon dioxide level, and this is controlled by our respiratory system. We will discuss later that we can hyperventilate to control the CO2 level, and this HCO3 negative, it is controlled by the kidneys. So the problem is that buffers are not permanent, they are temporary, they are first line of defense, they are temporary measures. Ultimately, the ultimate control lies in kidneys as well as in the respiratory centers that we will discuss in the upcoming lectures. So basically, in another way, if you want to see it like that these buffers, they act as sponge. Sponge can pick up water. If there is too much wet surface, it can pick up water. But if you place that wet sponge on a very dry surface, then it can release the water and make the surface wet. So this is just like that if too much proton is coming, it will pick up the sponge will pick up the proton. But if too less protons are there, then it can donate its own proton. But it cannot work indefinitely, just like a sponge. Sponge has its own capacity which might get lost. So it has its own capacity, and to regain the capacity, we need to do something, and that something is done by our respiratory system as well as our renal system that we will discuss in the upcoming lectures. So I think that was all for today's lecture. I hope I haven't missed something. Yeah, another important thing at the end that I would like to discuss, that what are the components of pH buffer. So pH buffers, we have two type of buffers. Okay, let me write it here. pH buffer consists of weak acid And now I am going to write something very complicated that might confuse you, that it consists of weak acid and salt of that weak acid with a strong base. Now, what the F is this? Let me explain it to you. So let's learn it with an example. Let's suppose we have a weak acid, again H2CO3, a common example. So if we have a weak acid and if we make a salt of this weak acid H2CO3, what is salt, by the way? Salt, in terms of chemistry, salt is the chemical which forms as a result of reaction of acid with the base. So this is weak acid. If we react it with a strong base, for example NaOH, a classical strong base, so this is a strong base, then what will happen? It will completely, this reaction will go completely to the completion. It will go into completion basically. So it will form NaHCO3 plus water. Now this is basically salt. So basically we have weak acid and salt of that weak acid with a strong base. So this is the salt. But Dr. Azaz, you have told me that in the previously you have told me that it consists of H2CO3 and HCO3 negative, and now you are telling me that it consists of H2CO3, the weak acid, and its salt, which is NaHCO3. What are you doing? Are you teaching wrong? Well, no. Actually, both of these things are similar. The NaHCO3 is a strong electrolyte. What I mean by this is that when it is thrown in water, it completely dissociate. Completely dissociate, I mean, what I mean by this is that almost all of it will form Na positive and HCO3 negative. So ultimately the end result is this, right? So even if we remove this, I can cross this like this, just remove this confusing part, and we can simply write it weak acid plus its conjugate base. It is technically the same. And you know, in textbooks you will written, in some textbook you will see it written like this, that it consists of weak acid and salt of that weak acid with a strong base. In other textbooks you will see it written that simply weak acid and its conjugate base, simple as that. Technically it's the same. It is ultimately going to form HCO3 negative, and if you are worried about what happens with Na positive, don't worry about it. It's the normal component of your blood, normal component of your plasma. When it comes to pH, it does not have any significant effect on pH. So again, it is a bystanderine. It is just lying there enjoying and seeing the show, that whatever is going on here. So a pH buffer can be of this type, which consists of a weak acid and its conjugate base in almost equal ratios, almost equal amounts, equal ratios, right? So one buffer is of this type. Then we have another type of buffer which I did not discuss much, but it also works in very similar fashion, and this is less common in our body. We have only one example. So the other type is, it consists of a weak base and conjugate acid of that weak base, conjugate acid of that weak base. So only example that I know of in our body is ammonia buffer. So ammonia buffer consists of NH3, which is a weak base, Along with that, we have its conjugate acid, NH4 positive. Now, what I mean by conjugate acid, as I've told you about the weak acid, that when it dissociates, it forms a conjugate base. Similar to that, when a weak base accepts a proton, for example NH3, it can accept a proton, and this proton, after it accepts this proton, it forms NH4 positive, and this NH4 positive can again release the proton. It can release the proton to form again NH3. So basically this is a reversible reaction. So it means when it is releasing the proton, it is acting as an acid, and so that is why this is conjugate acid. So I hope you got the concept. And by the way, some chemists also like to make the life of medical students a bit difficult. So they also write it like this, that it consists of a weak base along with salt of that weak base with a strong acid. Again, it's not complicated to understand. What if I write it like this? NH3 plus HCl. This reaction will go into completion and form a salt NH4Cl. Right now, this NH4Cl, what it will do, it will, in water, it will completely dissociate into NH4 positive plus Cl negative. The Cl negative is not going to do anything much related with pH. Actually, it has some effect in our body. There is something called hamburger effect and a few things, chloride shift, that we will discuss later, but forget about that for a moment. So this NH4 positive is actually simply the conjugate acid of that weak base, simple as that. And if you are confused how it works, it's very similar. Here the weak base is actually going to be acting as the acid fighting soldier, and this one is going to act as base fighting soldier. Here the roles will be reversed. It is going to act as base fighting soldier, and it is going to act as acid fighting soldier. Simple as that. It's not complicated. So yeah, I hope you understood. If you are still confused, I would highly recommend that you watch the previous lecture and watch this lecture again. But I have tried my best to make this complicated and chemistry-full topic less chemistry-full. I have made it a bit more tailored for medical students as compared to the chemistry people. So I hope you learned something. By the way, I have used so many analogies. So if there is a chemistry guy watching this video, he or she might get angry with me that, okay, this analogy is not very perfect. There is some technical nuances to it. It is not like that. Well, I know it's like that. It is not 100% accurate. No analogy is going to be 100% accurate. But for medical people, for medicos, these analogies, I think, would suffice, and they would be enough to help you understand. So yeah, that was all for today. I hope you learned something. Thank you so much for watching this video. Have a great day. Goodbye.